hundreds of miles. So, but practically there are losses, and so every X number of miles you'll have a receiver and a transmitter, so you have a booster station. But anyway, this is the whole principle but it works off the principle of Snell's law and total internal reflection. So that's a very long-winded answer to number 5, but it's worth spending some time on that because it's such a useful principle when it comes to things like fiber optics. Okay, number 6. Moving right along. Okay, the index of refraction of ethyl alcohol is 1.4. What is the speed of light in that material? Well, the speed of light is simply in a material is the pure speed of light in a vacuum divided by the index of refraction. So it'll be 3 times 10 to the 8th meters per second divided by 1.4. 1.4. So that would simply be 3 divided by 1.4 is 2.1 times 10 to the 8th meters per second. So it's slower. Okay, number 7. Light is traveling in a special kind of glass known as flint glass. If it encounters air at an angle of incidence equal to 20.1 and refracts at 35.7, what is the index of refraction? So what we have is and this is one way of measuring, a very good way of measuring the index of refraction. We sent a laser beam in here. Here's theta 1. Here, this is air, and this is the flint glass. And it refracts. So here's theta 2. Whoops. Okay, so N1 times sine of theta 1 equals N2 sine of theta 2. Okay, so we know that let's see, this is 20.1 degrees, so we do an experiment. We measure this angle and we measure this angle. Theta 2 is 35.7 degrees. We know what the index of refraction of air is, 1. So what's the index of refraction here? That's the question. Well, we simply plug everything in. N2 equals N1 sine of theta 1 divided by sine of theta 2. Whoops. We simply plug everything in. This is simply 1, and we get sine of 20 degrees divided by sine of 35.7 degrees, and and 20 degrees sine of that divided by 35.7 sine of that, and we get did I do that right? Whoops. Huh. Oh. You know what? I have these backwards. I have the angles backwards. If it encounters, this is the 20 degrees, I apologize. It approaches the air at the angle of 20 degrees, and it bends out at 35.7. I have this completely backwards. My apologies. It went the other way. we started from the glass, the ray started from the glass and approached the air at 20 degrees, and it refracts out at 35.7 degrees. So theta 1 is, in this case, 35.7 degrees, and theta 2, we still have theta 2 as 20 degrees. 35.7 sine divided by 20 sine, and I get 1.7. If you get it reversed, you'll get a number that's less than 1, which is what I was getting. So you can't have an index. If you get an index of refraction that's less than 1, you know you made an error. You made an error, and you probably got the signs, the angles mixed up, like I just did here. The index of refraction is equal to 1 or greater. It can never be less than 1. Because that would mean that you would have a, if you had a material with index less than 1, that would mean you have a speed of, the speed of light would be, the speed in the material of light in the material would be greater than the speed of light in the vacuum, which doesn't happen. Although, we'll talk a little bit about that maybe later. Okay. Because there is some claim, basically, that some physicists have been able to create index of, well, there are claims from physicists here and there that have been able to make materials that have the speed of light that's greater than the speed of the photon in a material that's greater than the speed of light in a vacuum. But that's a whole nother story. Okay, number 8. Number 8, we're getting back to lenses, doing 3 lens problems. Okay, so number 8, we have a converging lens that has a focal point that's 12 centimeters. The observer looks through the lens at an object, let's see, okay, the object is 3 centimeters from the lens, okay, and the focal point is 12. It's a converging lens. Here's the optic axis. Okay, again, I'm going to use the thin lens idea and just a straight line. This is the convex lens. And I'm just give a little bit of shape to it, but we're really going to bend it right on the straight line. And the focal point is 12 centimeters. So there's a focal point here and a focal point here. And the object is 3 centimeters. It's 3 centimeters to the left of the lens. Okay, now the first ray, ray number 1, is parallel in. And it goes through the focal one. So we go parallel in, and if you have a ray that goes parallel in a lens, a convex lens, it bends through the focal point. Okay, so that would be ray number 1. Okay, that's ray number 1. Ray number 2, I'm going to Okay. Ray number 2 is through the focal point and is parallel out. Okay. Okay, so that would be, here's the focal point. We can't go through, we have to go through this focal point. So we're going to go this way through the focal point. Okay. And then parallel out. Okay, notice already that these two rays are diverging. These are not converging. That tells you that they're going to be formed virtual rays back on this side, most likely. Number 3 is through the center of the lens. Through the center of the lens, and it's unreflected, unbent. Okay, so here's the center of the lens, and it goes through the center of the lens. Okay, so there's ray number 3. Now notice, on the right-hand side, all 3 rays are diverging. None of these rays meet over here, but they clearly will meet over here, but in a virtual way. Notice this ray here, if we take where the virtual ray is, goes here. If we extend that back, and then we extend this one back, and all 3 rays cross right here. So they converge right here. So at this point, again, this is the object, and this is the image. So the image is formed by virtual rays. Therefore, it's a virtual image. Okay, it's upright, and it's magnified. Okay, it's upright and it's magnified. Okay, so notice if you were looking at if your eye was over here, this is your eye, and you're looking this way. I can't draw a very good eye. And you put something on the opposite side of the lens, you're going to see it magnified. Again, you're looking over here, you're going to see it magnified. And so this is the idea, your basic idea of the microscope. You're looking over here, you put the object, your specimen, really close to the lens. It's way inside the focal point, but it's really close to the lens, and what you see is a magnified image. Okay, so it magnifies your object right there. This is the idea behind like if you have like a simple magnifying lens, this is exactly what you do. Okay, you're looking over here, and you're trying to magnify this, and it looks bigger. Okay, that's number 8. All right. Number 9, you have a converging lens. It's a converging lens that has a focal point 8 centimeters, and the observer looks through the lens. The object is 12 centimeters away. Okay. The optic axis. Draw your lenses as a thin line. It's a thin line, and I'm just going to keep it there. This is a converging lens, or convex lens. By the way, this is number 9. It is a focal length of 8 inches. Here, these are the focal points, and the object is actually 12 centimeters away. So that would be, always use your ruler when you do these. Here's your object. Okay? So the first thing, ray number 1 is parallel in. Oops. And through the focal point. So we come parallel in, and it goes through the focal point. Okay, that's ray number 1. Parallel in through the focal point. Ray number 2 is through the focal point and parallel out. Okay, through the focal, here's the focal point, we're outside of it. So now we can go through the focal point, and now we come parallel out. Whoops. Parallel out. Here's ray number 2. And number 3 is through, whoops, through the center. Through the center of the lens right here. And you can kind of see where these are going. In fact, I'm going to extend ray number 1. There's ray number 1. Looks like it's meeting way over there. And sure enough, here's through the center, and it's forming way out here in the corner. Okay, it's forming out here. And so the image is way out here. Okay, so this image, here's the image. Image is way over here. And the image is, it's a real image. Why do we know it's a real image? Because the light coming through the lens, all the light rays converge. So the image is real. Notice it's inverted. And it's magnified. Okay, and it's magnified. Okay, so this is a very common idea of, for instance, using like a telescope, where you're looking at something way out here that's small, or maybe a pair of binoculars. You're looking at something out here. What you're looking at is way outside the focal point of the lens. Focal point of the lens is out here, but you're looking at something beyond the focal point of the lens. It's way out here. And the rays come in through the light, but it's a real image, and it's flipped upside down, but it's magnified, and it's the magnification that you really want. Now, how do you have a pair of binoculars? Well, in fact, if you have a single lens telescope, you may have played around with this, you'll know that the image is inverted, or like it's a simple camera. This is also kind of like a camera. The image that's inverted in a single lens camera, the image that's on the film in a single lens camera is inverted for exactly the same reason. Okay, so how do you invert it, make it up? If you have two lenses together, basically the first lens inverts the image, the second lens makes it upright, and so at this point, if you have two lenses, the image will become upright again if you get the focal points, the focal lengths correct. So anyway, we're not doing combination of lenses. That's a more difficult problem. That's a problem to solve for a later time if any of you take optics like in college. Or just want to do it more just for the fun of it. Okay, number 10. Okay. A diverging lens has a focal point 8 centimeters from the center. The observer looks through the lens and it has the object is 5 centimeters from the lens. So the object is inside the focal point. Okay, this is a divergent lens. Here's the optic axis. It's a diverging lens, which I'm going to just use as I'll just do this to remind ourselves it's a diverging lens. That's a really bad way to did a bad drawing. Anyway, diverging lens using the thin lens approximation. Okay, focal point is 8. I'm going to expand that to 16 just for drawing it. Whoops, I did that wrong. 16. And the object is 5 away, which would be 10. Okay, here's the object. The object is inside the focal point, and we have a diverging lens. Okay, number 1, the first ray is parallel in and through the focal point. Okay, so we go parallel, the ray goes parallel in. Okay, but notice this is a diverging lens, so when rays go parallel in, they diverge out. And so, but it diverges out such that it's going through the focal point. So we line this up with this point, like this. Now, the way you know for sure is when you have a diverging lens, it diverges when the ray parallel coming in, it has to diverge. Okay, so, but it looks as if it's coming through the focal point on this side. Okay, for a diverging lens. Okay, ray number 2 is through the focal point and parallel out. Okay, so, well, the ray can't go here, so we have to act as if it's going through this one. We act as if the ray is going through here, but it comes parallel out. That is, it acts as if it's going through here, through that focal point, but then it comes out parallel. Parallel out. Okay, and we can extrapolate that a virtual ray back. This ray will look as if it's coming right from here, right along here. So that would be the virtual ray number 2 extended backwards. This is virtual ray number 1 extended backwards. Okay, number 3 is through the lens center. Through the lens center. So here's the center, and this ray just goes right through like that. Okay, so where do all these cross? They cross pretty much right here. So this is the object, and this is the image. But the image is formed by the converging of virtual rays. So it's a virtual image. Okay, it is upright, and it's smaller. Okay, it is reduced. Well, I hope this gives you a good overview of how to work these problems. Again, to work these problems well, you just have to do a lot of scaling. Use your ruler. Don't freehand these. Do not freehand these drawings. Make them as straight as possible using a straight edge. Measure them out, and these problems should work well. God bless you. Talk with you later. Whoops. Well, hello. This is the lab overview for Chapter 12. And this lab is focusing mainly on ray tracing and the index of refraction. In Part A of the lab, we're going to take a laser like this. You can see the laser dot, hopefully. And we're going to shine it through a piece of plexiglass. This plexiglass is about, it is about a 1/4 inch thick plexiglass. A sheet of glass could be used also, but plexiglass is safer. So what we're going to do, it's just a certain thickness. It's about, whether it is a width, is about 8 inches wide. I cut it myself, but the width doesn't really matter. But basically, we're going to do this, and I'm going to show you kind of what we're going to be doing. We're going to be taking the laser and shining it through, and I don't know if you can see this, but we're going to be shining it through the plexiglass, through the edge of the plexiglass, and I don't know if you can pick this up. Don't know if you can pick up the rays here, but basically we're going to diagram this. This is air. This is the plexiglass. Okay, and imagine the laser rays coming in like this. Here's the laser. Okay, we're coming in at an angle with the normal. Okay, this is, we're calling this theta 1. Now the ray would normally go right through. If the plexiglass were not here, the ray would go right through. So I'm going to draw as a dotted line the ray going right through. Okay, and we can easily approximate that by just, if we have the laser here in the plexiglass, we just tip we just tip the laser up a little bit, and it misses the plexiglass, and it hits right over here. So if we just kind of tip up just a little bit, we kind of tip the laser up, the laser goes above the plexiglass and it hits over here. Okay, but when we go through the plexiglass, Snell's law happens and it refracts. And here's theta 2. At this point, we have another normal, and it refracts again, coming out parallel. That is, this ray is parallel with this ray, and this now becomes theta 1 again. This is theta 2. This angle is the same as this angle, and essentially we work Snell's law in reverse, and we get theta 1. Well, what we want to do is, this is L. This is we measure this length of plexiglass, or we might this length, and we're also going to measure this, we're going to measure this distance from here to here. That is what we do. We're going to call this distance B. Okay. So we're going to measure L and we're going to measure B. So we can, when we send the plexiglass, when we send the laser through the plexiglass, we pinpoint where it comes out at this point right here. When we send the laser beam just a little bit above the plexiglass, we can see where it comes above the plexiglass, so we can measure this point right here. So we can easily measure this distance here. We measure this, and we measure this. Okay? And what I want you to do is using these measurements, and we measure this angle. We measure this angle right here, theta 1. Now we don't know what theta 2 is, but we can measure this, and so the whole idea here is to measure the index of refraction of the plexiglass.